The decision to use the repaired bracket, Bob's welded repair, rather than the CNC machined replacement, may have been the wrong call. Not because Bob did poor work. Bob's weld was exceptional. The reinforcing infills were, by any honest standard, better than what left Bugatti's factory. But a great weld is not the same as the right decision. The repaired bracket carries a specific risk that the CNC bracket did not. A risk nobody in the comments seems to be talking about. A risk that will not show itself at idle. It will not show itself on a gentle test drive around the block. It will show itself the first time Alex puts this Bugatti on a motorway and asks the W16 for full power. And by then, if that risk becomes reality, the car will be split in half again. Before I go any further, I want to be absolutely clear that this is not a criticism of Matt Armstrong. This is not a criticism of Bob. And this is not another voice claiming this rebuild was doomed from the start. What Matt and his team accomplished, without factory support, without documentation, without any cooperation from Bugatti, is genuinely extraordinary. Independent builders have never attempted anything at this level and come as close to success. But extraordinary work can still contain one decision that carries more risk than it needed to. The bracket decision is that decision. By the end of this video, you will understand 3 things. Why the repaired bracket carries a specific risk that no amount of skilled welding can eliminate. Why the CNC bracket, despite Matt's concerns about sensor positioning, was actually the safer long-term choice. And what should happen before this Bugatti is ever driven at full power. Matt's reasoning for choosing the welded repair was honest and clearly thought through. He knew the CNC replacement, machined from solid billet aluminum, would be stronger than the original cast component. No casting voids, no internal stress concentrations, uniform material throughout. Those are real advantages. But Matt's concern was also legitimate. The bracket carries 3 crankshaft position sensors. Sensors that tell the ECU exactly where each piston is in its firing cycle at every moment. Ignition timing, fuel injection, boost management, all of it depends on those 3 sensors reading correctly. If the CNC bracket places them even slightly out of position, the engine misfires. It loses power under boost. In the worst case, it does not start at all. Matt's concern was that converting a 3D scan into a CNC part introduces opportunities for dimensional error, millimeters lost in translation between the scan and the finished component. And that with no Bugatti diagnostic support available, getting it wrong could mean a car that simply doesn't run and no clear way to diagnose why. That is a careful argument. The argument of someone who has thought seriously about consequences and is trying to protect the project. I respect it, but it underestimates a different kind of risk. One the welded repair carries permanently, and one the CNC bracket would never have introduced at all. The risk is not in Bob's weld. The weld material itself, preheated correctly, right filler rod, properly executed, is stronger than the original casting. That part is not in dispute. The risk is at the boundary. When you weld a repair into an aluminum casting, you are joining 2 materials with fundamentally different histories. The original casting was formed under controlled conditions, poured into a mold, cooled at a specific rate, heat treated to achieve defined material properties. The weld material is different, deposited in a workshop, cooled at ambient temperature, with a different microstructure entirely. At the boundary between those 2 sits what engineers call the heat-affected zone. This is the region of original casting material that was heated by the welding process but never melted. It is not weld material, and it is no longer original casting material either. It is something in between. A zone where the thermal cycle of welding altered the microstructure and changed the material properties in ways that are completely invisible from the outside. Under gentle driving, low speed, light throttle, steady-state cruising, the heat-affected zone carries no significant stress. The bracket holds. Everything looks fine. There is no warning. Under dynamic loading, full throttle acceleration in a 1,500 horsepower car, forces cycling rapidly and repeatedly as the engine surges and settles, the heat-affected zone experiences something different. Fatigue. Cyclic loading stress that reverses direction over and over, loading the zone and unloading it thousands of times. This is the condition that reveals what the heat-affected zone is actually made of. Not one hard pull, not 10, hundreds and thousands of load cycles, each one small, each one adding to a cumulative damage total until, eventually, a crack initiates at the boundary. Usually without warning. Usually at speed. The CNC bracket had none of this. Machined from a single billet, it has a uniform microstructure from one face to the other. No welds, no boundaries, no zones where material properties were altered. The repaired bracket has 3 weld boundaries, and therefore 3 heat-affected zones. 3 locations where cyclic fatigue could, over time, initiate a crack. Bob's infill work added rigidity, and the weld itself is strong. But the heat-affected zones exist. They cannot be inspected away. They cannot be verified. They will only reveal their true condition under exactly the loading conditions a motorway run produces. This is the risk Matt accepted. I do not believe he fully accounted for it. Now, here's what I think gets missed about Matt's sensor positioning concern. It was solvable. The argument against the CNC bracket rested on the assumption that if the part came back from machining with incorrect sensor positions, there would be no good way to diagnose the problem and no path to a fix. That is a real concern in isolation. But it assumes the bracket would be fitted to the engine without any verification step, and that is not how precision manufacturing actually works. A CNC bracket, before it goes anywhere near the engine, can be measured. Every sensor position can be verified against the original scan data using precision instruments on a bench. Every critical dimension confirmed before any commitment is made. If a dimension is wrong, the bracket goes back to the CNC machine. The correction is made in software. The part is remachined. This is precisely what CNC manufacturing is designed for: iterative, correctable precision. The risk Matt described is real, but it exists only if you skip verification. A proper measurement step before installation eliminates it. Not reduces it, eliminates it. So let's compare the 2 approaches honestly. The CNC bracket, properly verified before installation, stronger than the original, free of casting defects, free of heat-affected zones, sensor positions confirmed with instruments. The welded bracket, heat-affected zones that cannot be verified by any means, cannot be eliminated regardless of weld quality, and will only declare themselves under full-power cyclic loading. One approach eliminates the risk. The other manages it as well as skill allows, but cannot make it go away. Matt has made his decision. The bracket is installed. The car runs. So the question now is what should happen before this Bugatti is driven at full power? And I think the answer is 3 things. First, a progressive run-in. Gentle loads to begin with, increasing gradually over weeks, giving any weakness in the heat-affected zones the opportunity to reveal itself early under controlled conditions rather than catastrophically at motorway speed. Second, regular visual inspection throughout that run-in period. A fatigue crack at a heat-affected zone is often visible before it propagates far enough to cause structural failure. Catching it early means a controlled repair. Missing it means something far worse. Third, close attention to crank sensor readings, any new vibration, any unusual sound, any fault codes related to sensor output. A propagating crack near a sensor mount changes the sensor's reading before the bracket fails completely. The ECU will often give you a warning if you are paying attention to the right data. If Matt follows those steps, the bracket either proves itself under progressive loading or reveals its weakness early enough to address safely. The dangerous outcome, the one worth avoiding, is full power driving before the bracket has had the chance to demonstrate that it is sound. The bracket decision does not define this rebuild, but it illustrates something important about independent work at this level. It is not only about skill. Bob has the skill. The weld is excellent. It is about having the time, the resources, and the margin to always choose the option that eliminates risk, rather than the option that manages risk as well as possible. Matt was working against time, cost, and the weight of millions of people watching. Choosing the known geometry, the repair that could be executed immediately, the option that didn't introduce new unknowns, that is understandable. But understandable is not the same as lower risk. The right to repair argument this entire project represents depends on one thing above all others: The car running reliably under full load, for years. Not just starting. Not just moving under its own power. The bracket will either prove itself or it will not. I genuinely hope it does. But if you have spent time working with welded aluminium under cyclic loading, you will understand why I am not fully confident.